as we looked at yesterday when we were exploring this, we saw that as time went on, we had this object dropping. We wanted the instantaneous velocity at the time when it was 1 foot off the ground. Okay? So that's what we were looking for here, is this instantaneous velocity. And what we're trying to find here is actually the rate of change. The rate of change we know is related to slope, okay? And what we're looking for particularly here is the slope of this line that is tangent to the curve at that point, okay? And we said that the key to doing this is bringing this other point that we're using. We were always finding the slope using that 1.561 as one of the points, but then we had, the 0.536, and then we had the 0.8, 29.76, and so on. And this point kept getting closer and closer and closer to the point that we actually wanted to find the slope at. And we said that as we bring this point closer to the point that we're trying to get the velocity at, this approximation of average velocity will get closer and closer and closer to what the instantaneous velocity is. And the reason for that is because our interval of time will be shrinking. We'll be taking that average over a smaller period of time. Okay? Does that make sense? All right. So, the whole concept here is this. One point is getting closer to the point that we want the derivative at, or the slope at. Okay? Here's this is a different function, but you can see the picture of what's going on here. We have this point x, f of x. And just like we did on the previous one, we have this other point, and we're finding the slope here of that secant line, and then of this secant, and this secant. Eventually, though, we don't want the slope of a secant. We want the slope of the tangent line. Okay? And what's happening here is we have this difference between our x-coordinates that we call h. And h, as the point gets closer and closer, h is approaching what? As we get closer and closer, h is approaching 0. Okay? The difference in the x-coordinates is approaching 0. Okay? So watch what I'm doing here. I have this point x, f of x, that I want the tangent at. I'm adding some value to my x-coordinate, so I have a second point, and then of course its y-coordinate is going to be f of dx plus h, and then we're doing the same thing that we were doing yesterday. We're finding the slope, okay? You guys know that the slope is the y-coordinate minus the other y-coordinate over the x-coordinate, x plus h, minus the other x-coordinate. Alright? So when we do that, notice here, x minus x is 0. The slope of the tangent line is going to be f of x plus h plus f, or minus f of x, all over h. But we want h to approach 0, and that's where we get this definition of a derivative up here. Okay? This is just a slope function with a limit as our delta x, or our h, is approaching 0. Okay? So that's our definition. We're going to look at a couple of examples of that today. But before we get to the examples, please note there's two types of notation here that we're going to use. Okay? One is this dy dx. Okay? That may be a little bit small, but we write it as dy over dx. Alright? if I remember right, this is called the Leibniz notation. You don't need to know the name, but dy dx. That just means the derivative of a function y with respect to x. Okay? That's going to become more significant if you go on and study some more advanced differential calculus. But for right now, just recognize that the notation means take the derivative. Okay? The other notation, I believe this is called L'Hopital's notation, is with this little prime right there. F prime of x. Both of them, again, stand for taking the derivative. Okay? Everyone with me so far? Okay. So, we saw yesterday pulling that point closer, taking the limit as the difference between the points, the x-coordinates gets closer to 0, will give us a tangent line, okay? So, as we consider that, let's start by trying to use this to find the derivative of one that we already know the answer to, okay? What kind of function has a slope that's always the same?
No constant.
What? A linear, and a constant function is a type of linear. So yeah, a linear function. So think about this. The derivative, if I gave you the linear function 3x plus 5, what should the derivative equal? Just 3. The slope, right? No matter what point we're at, the derivative will be the slope, and the slope is never changing on a line, so the derivative just equals 3. If you ever are given a linear function and asked to find the derivative, those are easy. Just write down whatever the slope is, okay? Because it's not going to change. That's what makes lines straight, okay? If you have a parabola, the reason why it's curved is because your slope is changing as x changes. Your slope can be written as a function of x, and we're actually going to see one of those here in a moment. Okay? So, let's start with one where we can already tell what the answer is. Here we have a line, f of x equals 4x minus 5. So already I know my answer for f prime of x should be what? 4. Let's see if we can get that though. Okay? And this will kind of show us the mechanics of how to use the definition to find a derivative for any function. Okay? So, you'll notice here when we're finding the limit as h approaches 0, we have this f of x plus h. This is the key part of this whole process, is figuring out what f of x plus h actually is. So, if our function is 4x minus 5, how would I find f of x plus h?
H is minus 5 and x is 4. No?
No?
You plug f of x into f of x plus h. I guess I'm confused. Okay. Whatever. Ignore that.
It's simpler than that. Instead of f of x, I want f of x plus h. So what do I have to do?
Maybe put x plus h instead of 4x, make it 4x plus h.
We're on the right track. Wait, put it as what?
And just substitute the x for x plus h.
There we go. We're going to substitute out the x, and we're just going to replace it with an x plus h. Yes, it's that simple, okay? You don't have to think too hard. You take this, okay, and you just plug it in for x, okay? That's all there is to it. All right, so we plug in x plus h to replace the x. We simplify it, so we have 4x plus 4h minus 5. Okay? Once you do that, really the hard part is done. Okay? Now it's just a matter of plugging things in and evaluating the limit. Okay? So, let's work our way through this here. We have the limit as h approaches 0 of f of x plus h. Well, we just found what f of x plus h is. It is 4x plus 4h minus 5. But it's not just that, it's that minus f of x. So it's minus the original function, 4x minus 5. Okay? And then that whole thing is over h. Okay? Everyone see how I plug those in? Alright, so let's start working on this, because right now, guess what? I have an indeterminate form. If I plug in 0 for h, I have 0 over 0. Okay? So, I'm going to simplify some stuff in the numerator and see what happens. Because I need to try to get rid of that indeterminate form. So, when I simplify up here, of course I distribute the negative. So I get 4x plus 4h minus 5 minus 4x plus 5 all over h. And now I have some like terms. Okay? So I have a 4x and a minus 4x. Those cancel out to 0, right? And I have a minus 5 and I have a plus 5, and those cancel out to 0. So check this out. Now I have the limit as h approaches 0 of, all that's left is 4h over h, which is still an indeterminate form, but what can I do?
Cancel the h's.
Now I can cancel out the h's. So now I just have the limit as h approaches 0 of 4. And what does that equal?
4.
4. Just like it was supposed to. Okay? Well, because I was evaluating the limit. And what this is telling me is that at any point on that line, the slope of the tangent line, or the slope is 4. Okay? Now, like I said, if you're given a linear function, please don't go through all of that. Okay? Use your understanding of the fact that the slope of a line never changes to just write down your answer. Okay? However, not everyone is like that. Here we have a quadratic function. And in this quadratic function, the slope is going to constantly be changing. That's why this one would look like this. Because the slope at this point is different than the slope over here. Okay? And it's different than the slope down here. Alright? So our slope will actually be a function of x. It's going to change as x changes. Okay? But the nice thing is the process here is going to be the same. Okay? So our function is x squared plus 3x minus 5. And the first thing I need to do is find f of x plus h. Good. Find f of x plus h. So, how am I going to do that?
Substitute x plus h in for x.
Very good. Here's my function. Substitute x plus h in for x. So x plus h squared plus 3 times x plus h minus 5. Okay? Oops. Here we go. Alright, so now I've got to do some foiling. There actually are not going to be any like terms, unfortunately. But we can still FOIL. X squared plus 2hx plus h squared plus 3x plus 3h minus 5. Okay? So that's what we're going to get if we FOIL all that out. And now we have f of x plus h. Okay? So that's the hard part. Now we get to do the easy part. You plug it in and get the limit. Okay? So let's do that. We need the limit as h approaches 0 of the f of x plus h that we just found here. Okay? We just found that. I'm going to cheat a little. There we go. So here's our f of x plus h. Okay? Minus the original f of x. Well, the original f of x was x squared plus 3x minus 5. Okay? And that's all over h. Okay. So, we're finding here dy dx using our limit. So now, let's distribute the negative and combine some like terms at the same time here to save ourselves a little bit of writing. The limit as h approaches 0 of what over h? Okay, so let's take a look. We distribute the negative to the x squared, and we've got x squared minus x squared, so that cancels out to 0. That's kind of nice. And then, hey, yeah, we distribute the negative to the 3x, and we have a 3x minus a 3x, so that cancels out to 0. Okay. And then, yeah, we've got this negative 5 minus a negative 5, so that's plus 5, so those cancel out to 0. All right? So what is left over in our numerator? 2hx.
Plus h squared.
Okay. So what can we do now? What, Leon? Divide out an h. Okay. Notice all three of these terms have an h in them. And that's significant because there's a common factor. So I can factor that out. So I have 2x plus h plus 3 left in the parentheses. And these h's cancel each other out. Okay? So now, that's what okay, so now we have the limit as h approaches 0 of of 2x plus h plus 3. And what does that equal? 2x plus 3. The h equals 0, so now it's just 2x plus 3. Okay? Does that make sense?
Yeah.
So it's a little bit of a process here, but it's not too bad. Okay? It's not too bad. Yeah.
Would the derivative then be 2? Or
No, the derivative is
2x plus
2x plus 3. So if I were at the point where x is 4, the slope is going to be 2 times 4 plus 3. The slope of that tangent line will be 11. If I'm at the point where x is 0, if I'm on the y-intercept, the slope of that line, that tangent line, is going to be 3. Okay? So yeah, the slope is changing as x changes. That's what makes the parabola curved. All right, so that's our answer. That's dy dx.
Mr. Nixon,
Yes.
could you go back a little bit?
Now, guys, what have you noticed? Every time we've done, well, both times we've done this f of x plus h minus f of x, what do you notice happens after we do that subtraction?
H comes out.
What?
The H cancels out.
The h will cancel out. Everything left over, notice, has an h so that we can cancel it out with the denominator. whenever you're finding the derivative of a polynomial, okay, other functions you have to use some other strategies for. But anytime you're doing the derivative of a polynomial, that's going to happen. Okay? All the terms that don't have h's should cancel out when you do the subtraction, and then you can factor out an h from what's left and cancel it with your denominator. Okay? Alright, now, the last 20 minutes here, I want to give you guys time. This is why we're in groups. Besides the fact Ms. Skokin already had the desk this way. But I want you guys to work on practicing with some of these. So let me point out a couple of things. Okay? Some of these have some radicals in them. How did you handle it when you had radicals and you were trying to get limits? You had to rationalize, okay? So you may have to rationalize a little bit with this and this, okay? You have others with some fractions, okay? These ones can be a little bit tricky, okay? So when you're finding the derivative, when these ones have fractions, one thing I would say is with your f of x plus h and your f of x, find a common denominator. And there's a couple of things that you could do with that, but you're going to want to get a common denominator. Okay? So, for all of these, find the derivative. Don't forget the definition. Limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? That's it. So let's go ahead and practice with that.